A man who needs no introduction. We'll see what Andy Nagy had to say 40 years ago.
The purpose of my brief talk is to demonstrate with the aid of some experimental data that in order to study and understand the dynamics of the neutral thermosphere, we have to have detailed information on the convection electric fields and the energy due to particle precipitation. I believe that most of you are familiar with what the calculated winds would look like if the only driving force would be that due to solar EUV heating. I only have a view graph of it, so not a slide, so I won't bore you with it. The winds predicted by such a model would be blowing from the subsolar point to the anti-solar point, modified by the Coriolis forces. So that means that in the northern hemisphere, just to orient you a little bit, we would expect the zonal winds to blow to the east in the evening sector and to the west in the morning sector, and the meridional wind would be blowing generally to the south in the northern hemisphere during the night. So now, what is really the situation, at least at high latitudes? The next few slides will show results of some measurements obtained about a year ago in Alaska, where we simultaneously measured ion drifts and neutral winds. The ion drifts were obtained using the Chattanooga radar facility, and the neutral winds were obtained by looking at Doppler shifts of some natural emissions, 6,300 angstrom emissions from atomic oxygen lines. Here are results from 5 nights in 1972, and these are supposedly vectors, and the circle around them is an indication of kind of the estimate of the error bar. I don't know if you can see it way back. And what it wants, this is to the north, south, east, west. Now, the point with this kind of mess of vectors, which is difficult to see, is that the neutral winds are varying from day to day. I mean, there is a significant day-to-day variation. But if you apply kind of an eye filter to this mess of arrows here, then the kind of thing that you see is that in general, in the pre-midnight sector, the neutral wind is blowing to the west and turning southward in the post-midnight sector. Now, again, as I said, there are significant day-to-day variations, but if you would kind of add them all up and get a general pattern, that's what you would find.
How do the 200-kilometer winds compare with the 120-kilometer winds that the radar derives?
Okay. Well, let me first clarify your question. Are you asking on how the 120-kilometer winds that the Roble-Hayes theory predicts, or no?
No, the 200-kilometer winds
Measured by the 6300 as compared to the 120-kilometer neutral winds derived by Oscar Brakke. I believe the general trend is similar, and however, there are very definite differences. But the trend, the general circulation, the trend of blowing. I need hands to talk. Blowing to the west in the evening, blowing to the east in the morning, and the general southerly flow. That general trend is there for the 120-kilometer winds also. But the numbers are, of course, different, the magnitudes and the details.
The winds themselves were made to match at 300 kilometers. It is tied in the vertical by a Yakia-type gradient, and therefore there may be significant deviations the further you get away from 300 kilometers. But it is locked in that position.
Let me clarify something, because I think you okay, what Ray's saying is correct, but I think he misunderstood Bill Hansen's question. Well, I think I answered your question. Now, what Ray is explaining about his model is that he really matched the ion drift and the neutral wind at 300 kilometers. Now his model is such that it predicts actually neutral winds at different altitudes, but on how good that prediction is as you move away from the altitude where you really did all this matching depends on how good your vertical profiles are on temperature and so on.
Your ability to reproduce the temperature and density profiles is really astounding. What solar EUV flux values did you use here, Ray?
Okay, I'm using twice Hinneregger solar fluxes, and I'm using an atomic oxygen concentration of about 10 to the 11th at 120 kilometers. So to make this model work, one has to tune the solar flux. The overall shape of the contours is really very strikingly determined by the neutral wind. So one very carefully has to evaluate what the component of the neutral motion along the geomagnetic field line is. And then the shape of the contours can be reproduced. In addition, the electric field also has an influence on tilting the shape of these contours, and this may make a contribution.
This really speaks well for what one can do with one-dimensional modeling, I think. Really.
During quiet times, perhaps.
I think it's only fair to point out also that there are many other calculations that, for which one has to double the solar fluxes as you did. Maintaining the global exospheric temperature in the neutral atmosphere, photoelectron escape fluxes, and other things also.
Yeah. Well, perhaps we will learn more from AE when it gives us results.
Rick decided to embarrass me and asked me to talk about myself, which is, and this, by the way, was at 8 p.m. Everybody was hungry and wanted to go to dinner, including me. It certainly wasn't my best talk I ever gave. But let me just start by saying, being asked to make some comments reminded me that Marshall Neugebauer, about 20 years ago or so, at an AGU meeting, told me that, Andy, at the committee meeting yesterday, we asked you to make a few comments. You stood up and said, I really don't have much to say or anything to say, and I was still talking 25 minutes later. So to avoid that, I kind of tried to put together something to say which is going to be hopefully very short. So let me start by saying during my career, I've been extremely lucky with both graduate students and postdocs. And this clip shows the example of that. Ray Robel was a graduate student, actually of mine, and Paul Hayes. And I don't think I have to say to you much about Ray, but just 2 months ago, he received the Bowie Medal from the AGU, which is the highest recognition that AGU can give to anybody. Ralph Cicerone was my postdoc. Now, probably all of you know that Ralph Cicerone has been the president of the National Academy of Sciences for the last, 7 or 8 years. So he didn't do too badly either. Now, kind of interesting, this meeting was in the 1974. The 1970s was a decade of transition for all three of us. Ray, many of you may not know, did his thesis. It was an experimental thesis. He built a 6-inch Fabry-Perot and made some measurements of the neutral temperatures and winds, which were kind of, it was a breakthrough, those measurements. After he graduated, he went to NCAR, became a modeler, and never touched a knob for the rest of his life. I mean, I think we made his life so miserable that he decided that no more experimental life for him. He'll become a modeler, a theoretician. By the way, the measurements that I talk about here were made by the 6-inch Fabry-Perot that Ray built for his PhD thesis. Now, Ralph Cicerone, some of you may not know, got his PhD in electrical engineering. And for his PhD thesis, he made radar backscatter measurements of the plasma line at Millstone Hill and wrote probably the first Monte Carlo model of photoelectrons. I hired him because I was very interested in photoelectrons, and we worked on photoelectrons for a couple of years. And without going into too much detail, we got a contract to help to write the environmental impact statement for the shuttle, and the solid boosters put out chlorine. So he and another postdoc of mine, Rich Tolarski, looked into the effect of the dissociation of freon, which leads to chlorine, what that does to the ozone layer. And that was quite a transitional thing in his career. And again, the rest is history. He never did photoelectrons again, and probably doesn't even know how to spell photoelectron anymore. But that didn't matter. He did very well. For my case, actually, I got my PhD in electrical engineering too. So for the first decade of my professional career, I was basically involved in doing experimental work on the thermosphere and ionosphere of the Earth. With Rick and Peter Banks, we got the idea at a picnic in La Jolla, about which led to Dynamics Explorer. So I was working on Dynamics Explorer very intensely in the 70s. But by a fluke of, and again, it's kind of interesting, but I'm not going to be talking for 25 minutes. By a fluke, I got involved in a mission called Pioneer Venus. And I didn't even know how to spell planet at that time when I started, but by the 80s, I kind of abandoned doing terrestrial, to a large degree, terrestrial aeronomy, and I started to work, and I'm still trying to, in solar system aeronomy. Which leads me to the final point I want to make, and I've been trying to make it for a number of years. Some of you may have actually heard me talk about it at CDAR tutorial meeting a couple of years ago, that if you do terrestrial aeronomy, you are well trained to do solar system aeronomy, and vice versa. I'm not suggesting that you should jump back and forth, but I want to make that point very strongly, and especially in today's difficult environment. You know, one can move if interest and need and opportunity arises back and forth. And I think the final thing I want to make is that since they were on the film clip here, I did say something about Ray Robel and Ralph Cicerone, but because they were at the 1974 meeting. But here with us today are three other graduate students, Ying-Jan Ma, Vanya Jordanova, and Mei-Ching Falk, who also didn't do poorly, and two postdocs, Tom Cravens and John Merriweather. So as I said, I've been very, very lucky in my professional career, and most of what I've done I owe to students and postdocs who worked with me. Thank you.